Hi friends, we're going to explore Ohm's law today. So go ahead and pause the video so that you can record this part in your notes, and then we're going to go through it. So pause now, draw this. All right, so remember that last time we took notes, we talked about current as being a flow of electrons, and I made the analogy of it being kind of like a river, the current of the water flowing. And the easiest way to think about this is like buckets of electrons and how many of those buckets pass in a given second, right? So we use the letter I to represent current. Now, I know what you're thinking, wait, why isn't it using an A to represent current since it's measured in amps and voltage is measured in volts and is represented by a V? But actually, current is measuring the intensity of the electrons that are moving through that wire point. And so we use I as a level of intensity for our equation of Ohm's law. All right, so what are our other variables? Remember, we have voltage, which we represent as a V. Voltage is the potential difference. We think of this as like the power source, right? So what else do we have? We have this guy. We have Georg Ohm. So you can cross that E out because it's not actually George. All right, so Georg was a German physicist who did many experiments to test his theories about the proportional relationship between voltage and amps, and he came up with this idea of resistance. Some of his experiments even included touching live wires in a circuit to see how much current or voltage he could withstand. And the payoff was having a law named after him, which is Ohm's law, and of course we use ohms as a representation for resistance. So we use a great big R for that. So here's the really basic principle. When resistance decreases, the current increases, which should make sense to you, right? Like if there's less things that are impeding the current's movement, then the current is going to go faster. But if there are more things that are going to impede the current or slow it down, so the resistance is higher, then the current is going to be lower. Okay, really basic relationship. So the law itself we represent as being voltage equaling current times resistance. And I would say this is probably the maybe second most important equation to commit to memory in physics. Maybe we have like E equals mc squared, and then we have V equals IR. All right, you need to commit this to memory. You will use it in physics. You will use it throughout your life. It is an important equation, okay? And I'm going to show you a really easy way to use this relationship. All right, so pause the video here, draw yourself triangles like this, and then I'll bring in my assistant to help me. All right, here she is, my assistant, my physics assistant, Pam. All right, this is so easy, even a lizard can do this. So whatever you're trying to solve for, your variable, if you are trying to solve for the voltage, say you have the current and the resistance, but not the voltage, then you just cover up the V here. Pam's gonna do it with her weird paw. And now I can see I need to multiply the current times the resistance, okay? Now, if I want to solve for the current, let's say I have the voltage and I know the resistance on my circuit, then I can solve for my current by dividing V over R. And likewise, if I want to solve for the resistance, I have the voltage and the current, I just cover up the R and I can see, hey, look, all I need to do is divide V over I, and then I get my answer. Really simple proportional equation, okay? All right, an important note is that 1 amp equals 1,000 milliamps. So we'll come back to that in a second. All right, so let's draw a really basic circuit. We've got our battery or our voltage source here. Remember our schematic diagrams. We have a representation of our current flow. I'm going to use an arrow, and then I'm going to label my current, and I'm going to label my resistor here. Okay, we draw the resistor like that, by the way, because it represents sort of the chaotic movement that the electrons would move through that resistor. All All right, so let's set up our variables. Let's say we have a 9-volt battery here. You guys know what a 9-volt battery looks like. It's the kind you put in your smoke detectors. All right, here's a 9-volt battery. I had one right here in my pocket. All right, here's my really simple schematic diagram of my circuit. I have my voltage source, I have my current here moving through, and I have my resistor. So let's say I know my voltage. I don't know my current. I don't have an ammeter on hand, but I want to solve for it. But I actually know what my resistor is. I know what the resistance for this is because many resistors are labeled. You can buy resistors to be 100 ohms. You can buy resistors to be 5 ohms. Resistors are in all of our electronic devices. So this is a 12 ohm resistor, and remember, I need to solve for I. So I'm going to do this really simple equation, which is 9 divided by 12, and I get 0.75 amps. Always include your units there, okay? Super, super simple. Let's try another one. All right, let's say I have my voltage, which I know is 9 volts. I know my current. I have an ammeter. I hooked it up to my circuit that I drew, and I know that my current is actually 0.039 amps. Okay, now I need to solve for my resistance. So remember, I can just cover up that R, and I can see V over I, and I can do this equation. Whoops, not that one. I can do 9 divided by 0.39, and I get 230.7, so really 231 ohms, okay? Now, this is measured in amps, and many devices that we use are actually measured in milliamps. So let's go back to this idea of 1 amp equaling 1,000 milliamps. If we want to convert this should take you back to the 6th grade conversions. Really straightforward. You're just moving the decimal place over 3 places. So go ahead and move that decimal place over, and that's going to give you 39 amps. So let's check our answer. We're going to use the simulator for Ohm's law. This is a good simulator to check your answers, and I think it's also a good simulator to play with and just kind of look at the relationship between voltage and current and resistance. And so you can drag these and change these. You can alter the resistance. So if you know 2 of them, then it will give you the output for the other. And your equation work should back this relationship up with the simulator. So the question that we solved together was 9 volts. So in this case, it's showing it as 6 1.5 volt batteries. And we actually know the current in our equation, but not the resistance. You can't actually change the current in this simulator, but you can alter the resistance so that you get the current that you desire, and then you can look and see what your current is. So if I start really high, so I have a really big resistance, my current's going to be pretty small, 9 milliamps. And I can move it down. Now I'm getting into 12. Remember, our current that we solved for was actually 0.039 amps, and when we converted it to milliamps, that was 39. So let's go ahead and try and get it onto 39. Got it. Okay. So it looks like now we have our voltage is 9 volts, we have our current at 39 milliamps, and that gives us our resistance, which is 231 ohms, and that really closely resembles our equation work that we just did in the video. So that worked.